So we're going to go ahead and get started on the second lecture here of this series. So what we talked about last time was the astroparticle lens, using particles from space to understand our world. And I talked a lot about cosmic rays as a part of that journey and the discovery of cosmic rays. Today, we're going to focus on muon tomography. So cosmic ray muons and how they tell us about our world. So this is an image that was taken from the Fermi Gamma Ray Telescope of the moon. So what you're looking at here is the moon shining in gamma rays. If you compare that to this image, which was also taken from space, which is X-rays, you can see completely different structure, right? When we change our lens, we get different observations. And then, as you know, the object, the moon, shines in the bright visible light, mostly because of the sun shining on it. And so what we talked about last time, and I just want to remind everyone on, is when we change our lens in the electromagnetic spectrum, we change wavelength, we can observe different things, right? We observe objects shining or not shining, and sometimes objects are opaque in certain wavelengths. And so we have radio waves, visible light here in the center, and as we go to the highest energies, we get to gamma rays. And we have X-rays here that was the curiosity in those images of the moon where it's shining in high energy gamma rays, but not in X-rays, right? And as we go to these higher energies for gamma rays and X-rays compared to visible light, we actually are probing smaller and smaller wavelengths, right? So we're talking about what we established last time was we're talking about smaller interactions on a smaller scale, right? On the scale of even a proton inside of the nucleus of atoms. So the moon and gamma rays, why is the moon bright? So we have cosmic rays that are mostly protons or charged particles. You guys can hear me okay, right? I just want to make sure this thing's not going in and out. So cosmic rays are high energy protons, and there's a sea of them that exists inside the Milky Way, and we live inside the Milky Way. The solar system's in the Milky Way. And so there's interactions of these cosmic ray protons across the universe that shines the Milky Way disk in gamma rays. And so we put telescopes in space like the Fermi Gamma Ray Telescope to measure and found this interaction. We said protons are colliding with gas throughout the Milky Way, producing gamma ray emission. But those cosmic ray protons are also interacting on the moon. And just like in the Milky Way disk, this produces gamma rays. And so what you're actually seeing when you look at the moon with the Fermi Gamma Ray Telescope is cosmic ray protons colliding on the moon, producing gamma ray emission. Okay? But why is the moon bright then in gamma rays? Why is it so bright that you can see certain regions of the moon that are brighter than others? And the reason the moon is so bright is because you have many high energy cosmic rays interacting, producing these kinds of gamma rays, and our detector Fermi Gamma Ray Telescope is sitting somewhere pretty close by. And the moon then is glowing in the gamma rays. The gamma rays make it to the Fermi Gamma Ray Telescope because it's so close to us, right? Because it's so close to our detector. It's unimpeded, right? There's nothing in the way. And you know this because you know of something called the line of sight. So this is a cool video I took that sort of illustrates the point, right? If you want to see an object, even a very far away object, you can't let things be in the way, okay? You have to have a nice line of sight. You can't have stuff in your way. Sorry. that absorbs the radiation you're looking at. So in visible light, if it's a cloudy day, you won't be able to see anything, right? And the things that are in the way will block your radiation, will block your light. When it's cloudy, you have light that's blocked. So this is a video that I took of the balloon launch in Antarctica from just this past season this is not the balloon we launched, but another balloon that was launched by NASA at the time. And you can very clearly see, right, that the balloon here at the top is lifting a small object, a payload, way up into the atmosphere very slowly. So I'm 10 miles away when I take this video. That's how far away I'm looking when I see this. But that's also how big the balloon is for these kinds of instruments, right? And the only reason I can see this if it had been a cloudy day, no, I wouldn't be able to, right? Line of sight matters here. This is an important thing. And in X-rays, that's what's useful, right? X-rays, we want to block that radiation. In fact, the moon doesn't glow in X-rays. Only 1/2 of it did in that photo, right? Because the side that was shining with the sun was the thing providing the X-rays, and the moon's surface is actually blasting the X-rays, reflecting them off the surface, and that's why we're able to see them, right? But part of the moon here, you can see part of the moon here completely opaque right, compared to the X-ray background of the universe. And this is actually what allowed us to make the discovery of X-rays in the first place. So the famous image of Röntgen discovering X-rays comes from the fact that he can make out different things in here because the dark regions are less X-rays being absorbed on the screen, and the bright regions are more X-rays being absorbed, right? So the line of sight here matters. Okay, so the way this was done, the discovery of X-rays now, is actually really interesting. And so we're going to talk about that. Excuse me. We're going to talk about that before we move into muon tomography. We're going to walk through the history of X-rays and how this all fit together. So let's go back to this device that was emitting X-rays in the first place that allowed Röntgen to make the discovery. This is called a Crookes tube. So you have a device sitting here that's emitting what are called cathode rays at the time. They didn't know that cathode rays were electrons. We'll look at that later a little bit, but basically they applied a high voltage, and a lot of cathode rays were making this Crookes tube glow. And so you have these cathode rays being emitted from a voltage at the time. This is like 1880s. Cathode rays going to a positive anode, and this is low pressure, and they can literally see the electrons. They can see the cathode rays, as they called them. Okay? And the cathode rays, when they were accelerated, the glass around the tube started to glow green. They're like, what the heck? Why is the glass glowing green, right? So Röntgen comes along and says, well, I want to look a little bit better at this green phenomenon, right? I want to see better what's happening to my cathode rays in the glass container here. So he puts a bunch of cardboard around it because he knows at the time cardboard blocks visible light, right? Maybe I can see better what's happening. And once he did that, he found that a screen nearby of some kind of material called platinocyanide, right, started also glowing green, even though the cardboard was there. And as soon as he turned off his Crookes tube, as soon as the cathode rays stopped going through the Crookes tube, right, no more voltage, no more green X-rays, ruined the spoiler X-rays, the green light here stopped shining on the screen, right? And so this was actually what was the discovery of these mysterious rays called X-rays resulted in the first ever Nobel Prize in 1901, right? Because no one had before seen things leaving cardboard box like that, right? No one had before seen particles that would escape the Crookes tube. The Crookes tube always stopped. The cathode rays were contained within there, emitting this green light. And it was purely accidental. He had no idea what was happening, and no one really did. But he was very systematic. He said, well, I'm going to investigate further this mysterious radiation. So he took a bunch of different materials, right, and he placed it in between the Crookes tube and his screen and found out that some thick materials didn't block the X-rays, didn't stop my screen from glowing, but something like lead did. So he put different books and different thick things like that. But thin pieces of lead actually did a very good job of stopping the screen from glowing green. And so this is how this is how he figured out that something that was happening was like the density of the material here is stopping the X-rays, right? Is preventing the X-rays from shining on my screen from the Crookes tube. And this is a groundbreaking discovery at the time. Not many other things in this stage in the history, in the late 1890s, no other phenomenon like this had really been observed, right? They could not explain it. The cathode rays they knew were contained inside that tube, and the visible light was being stopped by the cardboard. Something was going on. This is actually what inspired Becquerel to come by and discover radioactivity, as he was actually looking for these mysterious X-rays that everyone was fascinated by. Most of the fascination came from the fact that he could image some hand, right? He could show you that this was related to something tangible like the bones in your body. But at the same time, there was a lot of rapid development of discovery here for 10 years. Right? It was quickly determined that the X-rays were these mysterious but neutral particles. They couldn't bend them. So they knew that it was something mysterious, but they knew it was not charged. Right? They knew it was not like cathode rays. Becquerel actually thought that his radioactivity measurements were these fancy new X-rays, but later it was determined that some of those were charges, some of those were gamma rays. So wasn't the same thing. And so this led to a bunch of confusion, and everyone was very fascinated with the X-rays. Thomas Edison, in fact, was very, very obsessed for like 4 or 5 years with these X-rays. And a lot of his workers at the time in his lab were also very interested in the X-rays, so much so that they started exposing many different parts of their bodies to hundreds of hours of X-ray radiation. And some of his workers actually died. It was pretty sad. It scared Thomas Edison, and he said, he famously said, "Don't talk to me about X-rays, I'm scared of them." So this changed, though, in 1912 when it was finally discovered that these X-rays are actually the same part of that electromagnetic spectrum. They're the same kind of thing. They're waves like visible light is. And this was discovered by, and awarded a Nobel Prize by Max von Laue in 1914, where we used X-rays to image crystals, the structure of crystals. And later it was even used in the 1950s to figure out the structure of DNA. The reason you can do this with X-rays is because X-rays are small wavelength. They have the wavelength, the same scale, the same size here as the structure you're interested in. So in the crystallography, the separation between atoms in a crystal is about the same as the wavelength size of the X-rays, right? And so if you remember last time we talked a little bit about electron volts, the X-rays are high energy. They're over a kilo electron volts, over 1,000 electron volts. But the scale we're talking about is nanometers. And so this is the famous photo 51 that shows you actual DNA, X-ray diffraction on DNA structure. So that was the famous photo in the 1950s related to X-rays. So now we had an understanding of X-rays, but at the same time, cathode rays were mysterious themselves. And these two things are sort of linked, so I have to talk about both of them at the same time, because as the history and the understanding of these two things came together, so did the discovery of the muon. So J.J. Thomson famously looked more at these cathode rays, sort of saying, "Oh, okay, I'll let you guys look at the X-rays, but I'm more interested in these cathode rays themselves." And he put all of these cathode rays in different fields. They were also interested in magnetic fields and electric fields at the time. And so he calculated the charge to mass ratio of the cathode rays themselves. So the way this worked is he had to make a little bit of adjustment to the Crookes tube, so actually probably major adjustments at the time. He put these high-energy blue cathode rays coming in through a pinhole so he could block a bunch of them and focus them. And then he instrumented another electric field to bend those cathode rays, right, to bend the charges. And he found that he could calculate with both a magnetic field and electric field the charge and the mass of the rays themselves. And he did this, he discovered the electron in the process, right? He said, this is a fundamental particle. This thing, it doesn't matter when I change out the cathode here. I can put aluminum, I can put lead, I can put tungsten. I always get the same rays. I always get the same fundamental unit that has the same charge and the same mass. And this is this is almost a philosophical thing to these scientists at the time, right? Is it really the same for all matter? And the observation says yes, right? The observation is that this is just a fundamental particle of all materials. And this was what allowed him to discover the electron and get a Nobel Prize shortly after Röntgen in 1906. But then the question with these two discoveries at the same time, from the same contraptions, from the same understanding, is how do we get X-rays out of electrons in Crookes tubes? So Thomson, Röntgen, and others, right, changed the materials inside their Crookes tubes, and they measured the X-rays going through different amounts of material, right? They said, let's put different kinds of things in the way of the X-rays, kind of like Röntgen did, but inside the Crookes tubes now. And they were able to come up with an equation that sort of says, as you got some kind of energy, what we know now is the energy of the X-ray, you got more penetration. And so, for example, we got not so much penetration from muscle, we got not so much penetration from aluminum and a lot more from muscle, right? We could go through the muscle, but not the aluminum, right? More penetrating sort of meant to them higher energy of cathode rays. And so they started classifying all these radiation types with penetrating power. And this is probably historically why we also were doing this into the 1930s and 40s, is that this was the way to understand these different particles and types of energy, right? Was that how much material could they go through? It actually allowed them to sort of classify those materials themselves. And this is what ultimately resulted in the periodic table being organized by the charge of the nucleus of atoms, but that's beside the point, probably. So then along comes like the attempt by theorists to establish why the particles are emitting X-rays in the Crookes tube, right? And so one of the famous ones was Andrew Sommerfeld. So this is only in 1909. Arnold Sommerfeld. He I mean, you might know some of his students. He was a faculty in Germany. Some of his students were pretty famous, like Werner Heisenberg, Niels Bohr, and a few others, I think, at the time, too. And famously, like, I think 6 or 7 of his students won Nobel Prizes, and he never did. And so Albert Einstein said something along the lines of, I think I have it here. What I especially admire about you is that you have, as it were, pounded out the soil such a large number of young talents, which is pretty interesting to say to someone, in my opinion. But it speaks to how smart he was at the time, right? So Arnold Sommerfeld develops a theory here and says, can we explain why the X-rays are emitted by the cathode rays, by the electrons? And he said, well, if they're really charges, as Thomson discovered, then I know that those charges are decelerating. And so when they decelerate, they must be decelerating near other charges like the central nuclei or the atoms themselves, which also have electrons, right? And so this was coined the term Bremsstrahlung, or breaking radiation. So the animation shows you an electron coming close to an atom, where the green cloud there is the other electrons in the atom. And so this radiation is emitted as the high energy cathode ray or electron scatters off of it, and so it's breaking radiation. And the theory actually worked really well. There were spectrum of X-rays were observed. That meant that as you put in higher energy electrons, you could get more X-rays at different energies, right? And this also depended on the material, because those electrons were sort of related to the nuclear charge, right? And this also led to something that's very important for muons later, which is that the amount of X-rays you get is inversely proportional to the square of the mass of the charged particle that's breaking. So the electrons here are actually one of the lightest fundamental particles we know about. And so this 1 over m squared means that there's actually a lot of breaking radiation. There's a lot of X-rays emitted, right? Heavier particles, heavier charges like protons, even though they will emit breaking radiation, Sommerfeld says, his theory says, they're not going to emit as much. It's not going to happen as often. But there was some problems with this theory, right? One of the problems that was figured out was there was this weird feature at high energies where it would just cut off. And so this kind of plot shows you what they were observing at the time as they developed better and better detectors to try to see if Sommerfeld actually was right. They determined that the X-ray energy would steeply fall off here instead of rising for a very long period, for very high energies, as Sommerfeld said. And since it should go smoothly to high energies, Sommerfeld, the theory must be wrong, or we're not understanding what's happening with our Crookes tubes at some other level, like electrons are doing something special, right, that right now we can't explain. There were also some of these spikes that they started observing in the X-rays that were emitted, right? You have this emission that is like all of a sudden at one very specific energy. What the heck is that? And so at the same time, we come back to electroscopes, which played a huge role in the discovery of cosmic radiation. At the same time, scientists were figuring out another phenomenon. So in the 1890s, actually, around the time of the discovery of the electron, with these electroscopes, the way the electroscope works is you have these gold foil leaves just hanging there, and once you bring a charged object nearby, the gold leaves repel, right, because these leaves get a collective charge that's different than the than the charge plate up top, and so they start repelling. And what Hauck said was, if I shine ultraviolet light on the top here of my electroscope, I can force the leaves to fall, right? And what this meant was that electrons were being kicked out, or charges were being kicked out, simply from the ultraviolet light. And this was actually what led to the discovery of part of the discovery of the photoelectric effect. So it's completely reimagined what light and electromagnetic radiation were. So they're actually photons or particles now. They're not just waves. They don't just diffract DNA. They don't just diffract in crystals, They don't just diffract in crystals. They are particles. They're like billiard balls. And the photon energy, the X-ray or ultraviolet light energy, determined the electron that was kicked out, the energy of that electron. And so Einstein, as you probably know, proposed the theory to say this is quantized light. Light only comes in quantum here, in quantum packets, to explain this photoelectric effect. So the illustration shows you how we can explain the photoelectric effect. The X-ray comes in, hits the nuclear charge electrons, the nucleus there in an atom, hits an electron inside around the nucleus and ejects that electron out. And these two things are related and revolutionized our understanding at the time. Right? The electrons in atoms are in energy levels. This was not thought about until these kinds of investigations in the early 1900s. Right? And so the electrons in Crookes tubes are free electrons that are accelerated by a voltage, but then they're hitting the glass and making some kind of glowing green light, right? And they also had these characteristic X-rays. So these two particles, these two phenomena were entangled in history. The discovery of one led to information about the other and back and forth. And we had to refine our theories, and we had to understand, now what we understand is that the electrons in these tubes collide with atoms of materials. So since the electrons in the atoms are in these discrete energy levels, they can emit X-rays because, right, they are breaking, Bremsstrahlung breaking as they feel the atoms charge, the electrons in the atoms charge, right? And they have characteristic spikes because they actually sometimes, like billiard balls, bounce off of and kick out other electrons which emit radiation. So these two effects are now related, right, and result in us understanding the X-ray spectrum here. Cool, and so what they figured out was this high energy cutoff was determined by the acceleration of the electrons. If you applied a stronger voltage, you could get a much higher energy X-ray. But if you tried to shine, even though you left it on long enough, you never got above a certain energy, right? Because your voltage was tuned to that, right? That was the limitation, that was the understanding we needed. The other thing was that the kinds of materials you put in determined what kind of characteristic emission you got here, right? The kind of material that the free cathode rays were hitting also changed the characteristic emission of the X-rays. So the summary that we had was that electrons accelerated by a voltage allowed us to understand that the electrons are feeling the atoms, the electrons of the atoms, in a material, and they have this breaking radiation, right? And this breaking radiation is what Röntgen said all these X-rays emitted on his screen, that glows separately, right? But the cutoff and the understanding that the cutoff of X-rays in the energy of the electrons is related to the voltage that you apply. And then we had this other new phenomenon where the electron was accelerated by a voltage, but sometimes, right, the electron kicks out an electron in an atom. So this free Crookes tube electron hits the material, emits electrons, in the atom, and that electron actually emits different X-rays. And this depends on the material, right? So we had a good understanding of what was happening with Crookes tubes. And so by the 1930s, X-rays were a tool. We could look at this image and explain what was happening. We could say, sometimes we can't X-ray some materials. X-rays in atoms interact with the electrons inside. We have Compton scattering, so I said his name, so I'll check that off my list since this is his lecture series. So we have Compton scattering where those X-rays that are shining on this screen come into the atom and kick out an electron, but the X-ray survives, and so this is called Compton scattering. This is actually what happens to X-rays, and this also shows that they're billiard balls. This shows that they're photons, they're particle-like, they're not just waves, right? This tells you that they're bouncing and kicking out, like billiard balls, the electrons in an atom. And we also observe the photoelectric effect, where you shine X-rays onto a metal and you get electrons out, right? The X-ray and the kinds of electron energies you get out are purely determined by the X-ray photon's energy in the first place. Right? These things are linked, and this depends on the nuclear charge. So you can explain this image with the fact that, right, with these two ideas that X-rays over here are going through your skin, so it shines brightly because there's not so much charge there. But as you go to more dense material like bone, and the ring here, which has a much higher density than the bone, which has a much higher density than the skin, you get less of those X-rays through because the X-rays are starting to be impacted, or Compton scatter, or the photoelectric effect is happening. And this is actually why X-rays don't make it to the ground. This is why to observe anything in the universe shining in X-rays, we have to put our X-ray telescopes in space. So if you want to take this image of the moon, the only reason we could is because we put it in space. And this comes back to the idea of our line of sight, right? Even though there's many things that are shining in X-rays, the atmosphere is in our way. You can't just look, if you had been born with X-ray vision like Superman, you look up at the sky, you're just like, oh, that's boring, right? But that's obviously not boring. The rest of the universe is shining in X-rays. So this atmosphere is in our way, and these two things allow us to understand why that's needed. So going into the 1930s, we have a very interesting way of thinking about the way the universe works. We have an understanding that there's different kinds of radiation. We have electrons, which are like beta rays. We have X-rays, which can penetrate some things but not others. And we kind of know why, different densities, different nuclear charge of the atoms. And we have gamma rays, which can go through a lot more material. Right? We know that X-rays are emitted as this bremsstrahlung, this breaking radiation. Right? We know that matter is made up of positive protons and negative electrons, that those fundamental electrons in the cathode rays are actually inside, around the nuclei of atoms. This is all going in the 1930s. We know that charged particles radiate when they go through materials from that. That's how we got the X-rays in the first place. But the thing we couldn't explain was the cosmic radiation observed by Pancini and Hess, right? That I talked about last time. So if you're interested in that and you weren't there, I hear it's a phenomenal lecture from last time. And that also brings us back to the electroscopes, right? So a lot of people at the time said, maybe this cosmic radiation is just charged particles or gamma rays, and there was this whole debate. And it was very murky. I mean, when I look at some of the historical papers, it felt like there were a lot of identity crises, like who are we, right? We can explain all this, but not that. And the interesting thing was, Compton showed cosmic rays are charged and positive. He went around the world to do this, right? He took a lot of his friends on extravagant journeys and measured the charged particles, the cosmic rays everywhere, and proved they were positively charged. And other scientists at the time validated this theory. They said, yes, I can see that they're positive. One of those famously was Blackett, who constructed a very large magnet to bend the cosmic rays themselves. And I'm talking, is a very extreme, very strong magnet for the time. It weighed over 5 tons. And it gave you almost 10,000 Gauss, which is about a Tesla of magnetic field. So that's actually 40,000 times stronger than the Earth's magnetic field. If you want to really appreciate what this looks like, this is a picture from one of our instruments that detects cosmic rays nowadays. This black object is our superconducting 1 Tesla magnet on the Helix collaboration. And you can see my shoe floating there next to it. And this isn't some fancy trick, I swear. I didn't put my shoe there, take a quick photo, and then it fell down. This is my steel toe shoe just being held up by the strong magnet of our magnetic field, right? And that's also about a Tesla in this case, too. And so Blackett says, well, we can use these new ideas with detectors to investigate cosmic rays. This is around the middle of the 1930s. He wants to prove that these cosmic ray particles are positive once and for all, with trying to be convinced by Compton's measurements, right? So he develops a cloud chamber that is slightly improved by putting magnetic fields around them. He has a coincidence measurement where he takes 2 of these new technologies, the Geiger-Muller counter, on either side, and he says, let me put my cloud chamber, so you can see the cloud chamber going off here in the video, or you were able to. What did I do? That's better. So you can see the cloud chamber going off here. He puts a strong magnet in here. He has Geiger-Muller tubes to tell this around this chamber, so that when the cosmic ray passes through both of them, within a short time frame, he takes a picture of what's happening in his chamber. And this is how a lot of people at this time started taking tracks of cosmic rays, right? Started investigating cosmic rays. And then they took these contraptions all the way up to higher altitudes, because they already knew, right, from the balloon flights, that higher altitude meant more radiation, more cosmic rays. And this is actually how Blackett famously also confirmed the positron mass and charge that Carl Anderson had discovered a year before. So some of these cloud chamber studies give you wonderful photographs like this, right? This is one of Blackett's original papers here that show his strong magnetic field giving you these curved tracks of charged particles inside these cloud chambers, taken with this coincidence camera measurement, right? And so what he decided to do was, what he decided to do was count them. He said, I know which direction my magnetic field is pointing, so if I count the ones that curve one way versus the other, I can have a preference, I can see if there's a preference to have positive charges, which bend this way in the tracks, and negative charges bend in the other. All right, and so this actually meant that at the time we had a very good understanding of what happens with charged particles in this gas. We knew that charged particles in this gas ionized the gas, and that's what created the the tracks in the first place in cloud chambers. So a little diagram to help you understand this is a charged particle comes along and ionizes, kicks out the atoms nearby, right? And this is it's depositing energy, it's losing energy in the gas, which is important to our understanding of how to track particles in the cloud chambers. And Beta Bloch are other theorists at the time that famously came up with a way to say, we understand this so well, we developed this theory that predicts how much energy your electron will lose, depending on the material, depending on the density of the atoms, the charge of the atoms, depending on how fast those electrons are, depending on the charge of that electron. And this is a very successful theory. This allows us to say we can use the tracks themselves to talk about what kind of particle we're seeing in our cloud chamber pictures. And so we can go through and we can say, well, if Beta and Bloch are right, we can classify all these different tracks. We can say this must be a proton because it's a slightly thicker track. We can say that these are low energy electrons because they die, they have a certain path length here, and then they stop being tracked. They don't just disappear from the universe, they lose all their energy, right? And we even have a thicker track here, an alpha particle, for example. And this allowed us to say, when we put magnetic fields in here too, we could measure the curvature of those tracks. We could say, what's the charge to mass ratio of each of these particles? We became very sophisticated with this, right? We could say the charge sign, we could get the thickness, and get the energy. We know a lot about how to track these particles in cloud chambers. But we can't explain the cosmic radiation. This is the fundamental thing that led to the discovery of the muon, as far as I can tell, is that Blackett and others were counting these curved tracks. If they were positive particles in their pictures, they bend to the right in their magnetic field. And if they're negative, they bend to the left, right? Let's just go through and count the kinds of tracks we see. But this cosmic radiation was so penetrating, it couldn't be explained. It couldn't be a proton because it didn't match what we understood from the Beta Bloch equation from the ionization of gas. It couldn't be an electron, couldn't be a positron, right? And so some of Carl Anderson's cloud chamber trackers at the top of Pike's Peak here were very strong as well. They were over almost 8,000 Gauss, which is pretty close to that Tesla. And in this paper here, we have an electron shower on the right and positron shower on the left, curving in different directions, right? We're very confident what's happening. So when we take these photos, it's very hard for the community to say, these are new particles. These cosmic rays that we're observing are new particles. In fact, no one really could explain it. When Carl Anderson showed the tracks and said, look, I can tell you this Beta Bloch explains this one, magnetic field, this one bends this way, no one really believed that this was a new particle, right? And some of the original photographs of the muon, before it was known it was a muon, say, if it's a proton, it must be traveling upward. But that's not likely because I made sure my counters were in this certain configuration. I didn't get so many upwards, right? But I'm getting a lot of these guys, right? And so there were interesting things about if it's a proton, it must have very low energy, but that means it should have such a smaller, thicker track, or should die in the cloud chamber and lose all its energy, right? This is a very confusing time. And Robbie famously said this quote, which is something like, who ordered all of that when talking about the muons at the time in the mid-1930s? But they were found. Carl and Intermeyer investigated these cosmic rays closer, and they said, this is not an electron or a proton. It's something in between. It doesn't behave like either thing. But I'm seeing both of them. I'm seeing positive and negative charged things that have a mass that's not the electron and not the proton. It's somewhere in between, right? And so they proposed a new particle. They said the penetrating particles here, the two hypotheses are there's some other way for an electron to do things that we can't explain, our theories can't explain, or this isn't an electron at all. And with these strong magnets, they were able to measure the mass really precisely, and they found that it was 200 times more massive than the electron. And so Chicago was investing in this kind of effort too at the time. They decided, okay, we're going to build these. One of the news articles was building a very huge 12-ton magnet. I think it was just a competition of who could build the most massive magnet. But in the 40s, Compton also built a new magnet and had a new cloud chamber, new sophisticated detectors to try to understand what these muons are. And so finally, we come back to this excess. Were there more positive charges or negative charges of these cosmic rays? And so they studied these extensively. The one from the previous article, the apparatus here at Chicago, was these Geiger-Moeller tubes at the top and bottom, right? 2 at the top, 1 at the bottom, a cloud chamber in the center, and they actually have a big lead block that they can remove. They place it and they remove it to try to stop other particles from contaminating their data sets, but they also want to see the effect of that, of those particles, right? So they're able to calibrate against this. So they use this lead to filter out, and they were able to say, yes, there's definitely a positive excess, right? They can measure the energy of these particles and the counts for different runs of this detector series, and they get positive over negative by the right fraction, consistent with what Compton had seen with the east-west effect. So they were able to say there's more positive muons than negative muons. Cosmic rays, whatever they are positive charges, and some of them seem to be muons. But we didn't know yet about pions. We did decide to put these detectors up in space. So here's one of the high-altitude balloons that NASA does nowadays. So we put Chicago's nice Wilson chamber and Geiger-Moeller tubes up into space, basically, very high altitude, and measure particles up there as well. And we sort of say, well, cosmic rays come into the atmosphere, and they ultimately give us muons somewhere else at lower altitudes, but we don't know yet about pions, right? And this actually, so the muons themselves are much heavier. They don't radiate like electrons. Remember, the amount of radiation is inversely proportional to mass squared. The muons are 200 times heavier, so they emit much less X-ray radiation. That's why they can penetrate so deeply. That's why they can go further in materials. And so when we compare that to the other radiations, right, we have the muons having 1,000 times the energy and able to go through much more material. They don't care about the electrons and the atoms like the other radiations do. They usually have 1,000 times more energy, much higher energy than other radiation. But this new particle made sense to scientists at the time. It was more energetic, it was more penetrating, and it was able to always be there, right? It was always the cosmic radiation that was mysteriously discharging in different materials. Okay, so now we come to an interesting part of history with the discovery of muons and the theories that were proposed to try to understand them. We have muons decaying. So in the late 30s, scientists expected that muons would probably decay. They didn't know for sure. And this was because of a huge confusion. This is because there was this pion particle that a lot of people had been talking about trying to find, but no one could yet. And they thought the muons were the pions. So if you're confused, I'm confused too, because it's like these two things are not the same thing, but scientists at the time, I mean, think of how confused they must be, right? Because they don't know that pions do exist, but they kind of proposed them as a particle that would bind charges in the nucleus together. And so there was all this excitement about the muon, where it would be, maybe it was the thing holding the nucleus together. And so when it finally was determined that muons would decay, this was also done with cloud chambers, particles coming in and producing kinks where the thickness of your cloud chamber tracks would change shape. They would go from very thick to not so thick and much shorter. And this was an observation of muons decaying. But this was also famously used to prove that time dilation was right, because otherwise who could believe that guy Albert, right? So time dilation says that particles that are moving, or anything moving at a very fast speed, close to the speed of light, are going to have their clocks and their frame of reference move slower. And so the lifetime of muons is was the first way that this time dilation theory was validated. So this was done at Echo Lake. Here's a nice picture of Echo Lake. I would also like to deploy a detector at Echo Lake. It looks wonderful. But what they did was they had their detector at Echo Lake, which is at higher altitude in Colorado than Denver in Colorado, right? Denver's lower altitude by almost a mile, I think. And so at these different altitudes, they could measure the muons. And they said, well, the only way a muon has the lifetime we've seen and also makes it all the way to Denver is if it travels faster than a photon, which they knew wasn't the case, right? So one of the fancy diagrams you get is muons traveling much, much further than a photon can in the same amount of time. But obviously that's not the case. What's happening is cosmic rays, with their lifetime of 2 microseconds only, but traveling so fast, can live and go through much more material, can can stay alive much longer because of time dilation. And this was not the pion. The discovery of the pion happened, a little bit later, like 10 years later, after World War II was over, really, because of development of new detectors where they actually saw the pions being made. So they got so good, I think I talked about this last time too, they got so good at measuring particles and tracking particles, they developed these nuclear emulsions to image what those tracks would look like at a very short time scale, and got good enough to see that, pions are being made. The way this works is protons come in, the cosmic ray protons come in, hit our atmosphere, make pions, which produces muons. The pions decay to muons. And so here's where even newer technology must be invented. Sorry. So newer technology must be invented. I keep doing that. You wanted the microphone. No, I'm just joking. So newer technology must be invented. And Luis Alvarez, who was actually a student here of, you guessed it, Compton, at University of Chicago, invented the hydrogen bubble chamber. And he actually helped prove that muons aren't interacting with the nucleus. These pions that we discovered are in fact the actual particles. So these two things sort of went hand in hand, right? And the hydrogen bubble changer was sort of a game changer in the study of what's happening with nuclear collisions, because it allowed us to find resonance states of different nuclei, which is actually how he was awarded the Nobel Prize in 1968. But Luis Alvarez had a very, very interesting life. He was a part of the Manhattan Project, and before that he was working with Fermi. Before becoming a part of a member of Manhattan Project at Los Alamos, he actually helped Fermi with other projects too. And at the time he also worked with the British to develop what's now, I guess, the ground-controlled air method controllers, right? So this is what allowed him to sort of become very famous. He was very interested in solving a bunch of different problems and aided a lot in the war. And he has a very interesting life. Here's him with his bubble chamber at University of Berkeley later after World War II, so this is like 50s and 60s. And he also was actually not on the Time magazine cover in 1961. So I don't know if you guys know this, the 1961 Time magazine named the Person of the Year as a bunch of scientists, I think it was a set of 15 or so. And Luis Alvarez was not on there, but that's okay because he actually was awarded the Collier Trophy by President Truman. So take your pick. Which one do you prefer, being on the cover of Time magazine or getting a trophy from the president? So not so long after the bubble chamber not so long after World War II, is when the way we're thinking about muon tomography comes in. Right? So we take our Geiger-Müller tube, or counter, and E.P. George, a physicist in Australia, says, I have a good idea. I'm going to put it above and below a tunnel. I'm going to count the number of muons that I'm measuring above this tunnel and below it. And he says, if I detect less muons below, I know the reason why. I know that these muons are losing energy in this material. And the way they do is the beta-Bloch equation, right? I know that this should work. So the muons coming in are just always there. I don't know where my mouse is. The muons that are coming in are just always there. And so if I count them up here and I count them down here, I get less muons. And so this idea was sort of novel this is like the mid-50s, is pretty novel, even though we understood muons so well. I don't think there's any reports of anyone else thinking about muons this way. So remember, the beta-Bloch equation tells us we know how muons lose energy over distance, and they depends on the material. And we also know how many muons there are. So this is a plot of the muon flux versus depth here, and this is sort of like summed over all different energies of muons. So right now, we can calculate with this vertical flux the number of muons passing through an area per second. And the way you want to think about flux here is just the number of particles going through a given area in a specific, in a set given time, right? And right now, for example, since you're inside of a building, I think I accounted for that, right? If you're inside a building and most of the muons are coming at you from above, you only get about 10 muons through each of us every second. So it's per person, not total. And so the cosmic ray muon measurements with density was sort of a novel thing. You could make a measurement of what's called the opacity, right? And so the opacity is just a measure of the reason that we're seeing less muons is because of all of the density along the thickness of a material, right? The thicker the object is, the less muons you'll get. But also, if you had the same thickness of two different materials, the denser one would give you less muons, right? All those muons would lose energy throughout. And so this example shows you for soils, right, which is one density, what kind of depth you can get and how many muons will be removed, the attenuation factor. So if you start up here, you have just a factor of 1. You have the amount of muons you see, right, going through basically no soil. But as you go to 2 or all the way up to 100, right, you get actually around 1/100th the number of muons, right, through this a thickness of 100 meters of soil. And this was how E.P. George was able to calculate. He said, I'm going to estimate then the density because I know the distance of this from the top of this tunnel to this edge where I'm measuring. I can calculate for you the density of the soil inside. And so then there were also samples brought in. People came in and took samples of this soil, and the comparison, the measurement was that it was about 2%. Right? So that's actually pretty impressive. These muons are just sitting there. We know them so well. We were able to utilize the information we gained, the way we thought about muons, all of the history of developing and understanding of what's happening to cosmic ray muons allows you to say, I can know confidently, and I can detect them confidently enough to measure the density of the material that they're going through, right? And this was the first attempt at muon tomography. So Louis Alvarez was actually inspired by this very measurement, and he said, well, let's use this to study the pyramids of Egypt. And so one of the paper that mainly came out of that here is Search for Hidden Chambers in the Pyramids. This was actually, what happened was they came up with all these detectors at Berkeley around 1965 or so, and they deployed them, I think in 1966, to the pyramids in Egypt, just south of Cairo. And then there was the 6-day war that broke out, and so they sort of had to take everything and go back home. So they didn't actually, the first time out, they didn't actually get to take any muon measurements. But by 1970, they had finished all their measurements, and they surveyed 20% of the volume of these pyramids with their muon detectors. They didn't actually find any hidden chambers, and they used a new technology that was sort of in the evolution of particle physics detectors very important, which is the spark chamber. Basically, a spark chamber tracks your muons, right? And so a muon coming in here, here's a picture of one of the spark chambers used in there. You can see the word danger because of the high voltage that was being used. So a muon comes in, and then they can track the muon in different layers inside of these spark chambers. When the muon ionizes gas in different layers of the instrument, it's at a high voltage, it releases a spark, and that flash is what's recorded in the thing. So this is actually, when they deployed these spark chambers to do this tomography of the pyramids, they let them sit there for a year to take these kinds of measurements. But they did prove that the idea worked, and it worked pretty well. So here's a diagram from the paper that shows what one of those pyramids looked like. And they put their spark chambers in in the tunnels below here at point B, and they said, well, we can, with all of our muons coming in, we can say the line of sight, the number of muons that are blocked, right? We know how to quantify that, and it doesn't match the assumption that the pyramid has a smooth surface. So if you assume that this pyramid is just a smooth distance here that you know that you've already measured, then you can calculate what the density was. And since what they found was a deviation, they said, well, from an angle, this is versus angle, so it's not exactly what I would have liked to show to you guys, but it just says at these angles, there's a deviation from the expectation that it's flat, right? There's more or less, there's less muons coming from this direction, right? And that actually matches exactly where the known limestone protrusion sits at the top of the pyramid. And so this is proof that the idea of muon tomography, right, of looking at the line of sight of muons with detectors below and having an understanding of how many muons are passing through a material through a given area per second works. All right, so So now we can fast forward to some other really awesome examples of how muon tomography is used. So for example, with glaciers, the interesting things are how much ice coverage do you have on top of different mountains? The volume of glaciers in certain regions is actually pretty hard to probe because they're in sometimes remote areas. So the comparison of densities here, we're talking about ice, which is more like 0.9 grams per centimeter cubes, and for some glaciers it's much denser. It's closer to rock. It's like 1.3 or something. But the rock itself that the glacier is on top of has about 3 grams per centimeter cubed. And this difference in density allows us to measure different amounts of muons if we put the detector somewhere below, right? So one of the examples that was done in the Swiss Alps, right, is where we reconstructed the bedrock shape underneath the glacier because of this density difference from the ice on top of it. And so this is a reconstruction. Each of these sites shows the location of a different muon detector in a tunnel below one of the Swiss, below Mount Eiger in the Swiss Alps. And so what they found was that their muon flux versus obstacle thickness, right, if there was only rock, would follow these lines, but the data points show that there's an overabundance of the thickness, right? There's more material there, or there's less material there because we observed a higher muon flux in that region. And this imaging took 100 days. So there's 100 days of muon data taking to make this kind of map of the glacier and the bedrock. So you can think about this muon tomography, for example. On the right, we have cosmic ray protons interacting in the atmosphere, pions. We didn't really talk about those, but they're there. And then you get muons down here, and these cosmic ray muons are just always sitting there, so you can measure them. This is the exact same thing, almost, as when you need an X-ray done in a medical lab, right? You have an X-ray generator producing all of those X-rays, and you put the thing that you want to image, the tomography you want to make of, below, and you detect the X-rays that are blocked, and you get these kind of radiographs. But then the doctor tells you have to sit there for 100 days. And you're not going to do that, right? Because this isn't muons, this is X-rays. These are pointed, in this case, pointed light, right? This is a bunch of X-rays, a much larger flux going through your bone. But the whole thing relies on the fact that the line of sight is what's happening, right? You have less muons making it through different materials and how much. And so we developed more sophisticated detectors for other particle physics reasons that are now applied also to the muon tomography, to fields around muon tomography. So we went from Crookes tubes, right? Sort of like our screen, we use a scintillator. And actually, if you look at the screen, the barium platinocyanide that was what glowed green in Röntgen's original discovery of X-rays, the scintillator here, that was also a type of scintillator. So modern day scintillator is sort of borrowing from the fact that that was glowing green at that time. It's the same idea as that the particles were glowing green in this case. So you have the way a scintillator works now, or the way a scintillator works in these detectors, the muon being a charged particle, comes into your material and emits a bunch of optical light. We also developed a way to quantify and count the light flashes without taking camera photos of the tracks, right? We developed what's called a photomultiplier tube. And this actually borrows, or is fundamentally relies on the photoelectric effect, which was also part of the X-ray and electron journey at the beginning, right? You have incident light coming in, and in the photomultiplier tube, it hits a certain kind of material, and that material emits a bunch of electrons, and those electrons are the voltage that you measure, right? So that's how more sophisticated detectors work nowadays. So the whole way, the flow this works is a proton comes in, produces a muon, goes through your scintillator, produces light because of the photoelectric, because of the scintillator, and then that light hits your PMT, and because of the photoelectric effect, gives you an electron, and that's what you record in this last part, which is called your data acquisition system in the business, right? So now, fast forward, 50 years after Luis Alvarez's first attempt at imaging the pyramids, right? We put these new sophisticated detectors in the Scan Pyramids project and had more than 50 days of operation. And in this time, they did a different thing than Alvarez did. They didn't leave the detectors in one location the entire time, right? In location B of that image underneath of the pyramids. They put them around the pyramids in different tents and different configurations and made multiple measurements, right? And this allowed for both the thickness of the material to be measured because of different locations, giving you sort of a view around the detector of the density profiles through it. And this was actually an international team with all these different new detectors. It was a very exciting, it sounded like a very exciting adventure with muon tomography. One of the fantastic scientific and human adventure. I agree with that. Reading about it was very enjoyable, actually, too. And you can see from the scanned pyramids, what they actually found was that they were able to determine the known void or cavity, as it was called in the paper, C1 here, at the top of the pyramid. They were able to prove that that was also what they found with muons. And there was a void that no one had ever known about in C2. There's this big gap inside of the structure of the pyramid that no one had been able to say was actually there. And was this interesting to other scientific communities about the pyramids? I mean, I look at it and I say that's very interesting. Here's a picture of where the voids are in a 3D constructed map. You can see point I as these regions of, doesn't really show up well, sorry, it's red and green here, and the different tunnels and known locations inside of one of these pyramids is shown. At first, some people, especially in Cairo, didn't really think it was that interesting. There were conflicting accounts of whether this was an interesting discovery to Egyptologists. It sounded like, I think one of them was, they found nothing. This paper offers nothing to Egyptology, 0, which is ridiculous in my opinion. But then the next, I think it was over 2 days later, the same man said, this was a major discovery that would enter houses and homes of people all over the world for the first time. So it's not clear to me. I'm not an Egyptologist, so I can't say if it's interesting. It sounds pretty interesting to me, but obviously I like particle physics, I like muons, so that's probably where I'm a little biased, right? So then another project that's interesting with these cosmic ray muons is volcanoes. So this is called the Mu-Ray project. And so this volcano is it's pretty famous, you probably know this volcano, is Mount Vesuvius. And the way this works is you place your detector on one side of the volcano, and you have these cosmic ray muons coming through, and you can get these density image profiles of the muons. And this was actually done before the Mu-Ray project. This was actually done in 2009 or so with Mount Asama, if I'm saying that right, in Japan. And this is a really interesting study with muon tomography. This is an actual observation before and after of a magma chamber, before and after mass loss, before volcanic eruption. And so what they were able to say was that there was an estimated amount of 60,000 tons of material removed from the chamber. So you can see the images they had produced before for about a month of observation. And then the image of, I think it's a couple weeks after, this is the eruption happened and then only a couple weeks of observing. And they can see a significant difference in the amount of muon flux coming through. And from their muon flux only, they were able to calculate the amount of mass loss, which was about 60,000 tons. But obviously, volcanologists also go through and measure the amount of volcanic ash that's emitted from different images and photos and things and other techniques. But they were able to say that that was closer to 50,000 tons. But it's amazing how close that is, actually, right? Because this muon tomography does not make any estimate of other than what's the muon flux, right, with the detectors in these different sizes. There's also one project that I'm really excited about to see the results of, which is using muon tomography to study tornadoes. And so what's interesting about tornadoes from the standpoint of meteorologists what's difficult about understanding tornadoes from the standpoint of meteorologists is the air density profile. There's actually really no way to measure directly the density inside of a tornado, or even the supercell that's making a tornado that the tornadoes are inside of. And so here's a picture of how this works with muons, where these muon cosmic rays come in, you place your muon detector here, and you can image the density profile from other directions as well, but you're mostly interested in what's happening towards it. So as the density of the air changes, because of the amount of flow, the temperature changes and things like this. This is a gas, it changes with temperature. We can make a measurement using cosmic ray muons, right? We can make a measurement of that density. And so the preliminary results, I think this was only a few hours of observing in Missouri, I think a little bit over a year ago, maybe, or about a year ago right now, I think it was March of 2025. The results published show that it might be a thing we can do, but we have to do a little bit better at building the kinds of muon detectors we want for this. So stay tuned on tornadoes. And so then I want to come to another phenomenon that we're able to use with muon tomography, which is not the one where you lose where the muon loses energy and so you observe less flux. This is actually called multiple Coulomb scattering. So in multiple Coulomb scattering, the muon comes through an object and it's scattering really because of the electrons, the charges of the atoms inside. And in that regard, if you actually measure a muon above and below an object, you can measure the deflection of that muon. And we know really well, actually, how this works, how we can say, because it's really a muon of some known energy, right? We can say what happens to it in a kind of material we want, where it deflects off of the atoms of the muon. And we can say how much displacement from no deflection to deflection we have. We have a good understanding of this in a bunch of different kinds of materials. So you can actually do what's called scattering tomography, right? Where you make a measurement like this and show that the object was in a certain location because you got more muons or an absence of muons because they were scattered by that material. And this works obviously just like, I should have said this before, this works for both muons and antimuons. We're just talking about a total muon flux for both of these things, right? And so this is kind of like if you were to, what you do in the medical field too, I guess, where you have an X-ray detector and the source and you sort of rotate them, right? You say, I want muons coming from this direction and that direction. You sort of want to make a 3D map of what the object is. Okay, so there's some improvements that are ongoing in the field of muon tomography. So one of the scan pyramids, they plan to go back, I think, is what it sounds like, to do, but with new detectors that they developed, using this multiple Coulomb scattering on different parts of the pyramid, I think. And one of the things they prove their new detectors does in this multiple Coulomb scattering configuration, with this configuration of lead blocks, after 5 days of observing the muons, they can reconstruct what those lead blocks look like, which is a fancy smiley face. But also with the multiple Coulomb scattering, you can actually make a measurement of the different kinds of material, is what it sounds like is also something that's sort of ongoing investigation and looks promising, which is, in this case, a bunch of different blocks of different materials are used in these muon detectors above and below, and you can say more muons scattering, less muons scattering, right, depending on the nuclear charge of the material. So there are some limitations. I don't want you walking out of here thinking, oh my gosh, I can do whatever I want with muons, right? There are some limitations. I mean, this is a huge feat of particle physics, which is you need a large detector area. As we said, you don't want to sit there for 100 days, right, to image your arm, basically, right? You're not going to do that with muons anyway, but one of the takeaways is you need a large detector area. And so you need detectors that are able to get all different directions and get this large muon flux, right? You have a low flux of muons at some of the energies we're interested in. So one thing I didn't really talk about is that muons at higher energies, since they go through more matter, might be more interesting, but at higher energies, there's less of them, right? And it's actually steeply falling. There's one to every 10 times energy, there's actually 1/100th of the muons there in the first place. And if you want to do muon tomography with even thicker things, you need even higher energy muons. But you also need detectors that have good spatial resolution to extract the particle direction, for example, and you also need deployability. All right, you need to be able to put these detectors in tents around pyramids or near volcanoes out in the wilderness, right? So make them compact and transportable. But it sounds like there's a lot of awesome, interesting things to come from cosmic ray muon tomography. From things that we talked about, like volcanoes and glaciers, and using tunnels. We talked about the pyramids, but then even things like being able to scan cargo for dense materials as well. So I just want to leave you with, this sort of appreciation that this deserves, which is that we understand so well that cosmic rays are these high energy particles coming from everywhere in space, from different exotic environments and extreme environments, right? And we live in a sea of those cosmic rays, and they come to Earth, and they collide in the atmosphere, right? The cosmic ray, they collide in the atmosphere, and as they go down to the surface, they produce a bunch of muons, right? So up here, you're living in the sea of cosmic rays, and down here, on the surface of Earth, you're living in the sea of cosmic ray muons. And we build detectors here to detect those cosmic ray muons, which allows us to X-ray volcanoes and other wonderful thick structures. But we just have to put on our astroparticle lens. Thank you. Okay, I'll take